So, why do reactions occur at all? In organic chemistry, why do reactions occur? For example, if we have a beaker with these two compounds, why do they react? We know they react for forming bonds, but why? So, for example, let's say we have this hypothetical X compound and this hypothetical Y compound. Usually the reason why reactions occur is because this X compound has this localized negative region, this negative charge density region. And this Y compound has this localized positive charge density region. And we know nature hates highly localized, highly chargedly dense regions. We know that's unstable. Nature hates those chargedly dense regions. However, we have this negative compound in this positive compound. We know they can react. These charges will attract each other. Now we know they can go through a reaction. And when they go through a reaction, forming this bond, we know the charges destroy each other. These charges will neutralize each other, destroying those charges. So now that they've neutralized each other and destroyed those charges, now there's no charge density regions. Now there's no charges, no highly charged dense region, so we know that's stable. And that's 99% of the time why reactions occur in organic chemistry. There's one compound with excess negative charge dense regions and one compound with excess positive charge dense regions. And in organic chemistry, the terminology we use for these negatively charged regions are nucleophiles. And the terminology we use for these positive atoms with these positive charge regions are electrophiles. And 99% of the time, that's why we have reactions occur in organic chemistry. For example, if we had a beaker of, let's say, these two guys, why do they react? Because this guy has some negative charge dense regions, this guy has some positively charged dense regions, and that's not stable. This localized negative charge and this localized positive charge isn't stable. However, when they react, those charges destroy each other. So now there's no charge dense regions, so that's stable, that's energetically favorable. So these are some examples of nucleophiles with these negative charge dense regions, and these are some examples of electrophiles with those positive charge dense regions. So, but not all nucleophiles are the same. For example, let's say we're comparing this nucleophile with this nucleophile. Which of these is a stronger nucleophile? Well, again, if this has a formal charge of -1, and this doesn't have a formal charge of -1, we know this is a stronger nucleophile. We know overall they're very similar. However, whenever we have a formal charge of -1, we have more localized negative charge dense region. So that's a more stronger localized negative charge, so therefore that's more unstable. So this really wants to react, and therefore this is a very good nucleophile. So how about let's compare these two nucleophiles. Which is a stronger nucleophile? Well, this has this negative charge dense region, but this one also has a formal charge of -1, so they have the same amount of negative charge. However, this guy has resonance. There's resonance stabilizing that negative charge, delocalizing that negative charge over a larger region, so there's a smaller charge dense region. Here, the negative charge is all localized on this carbon. Here, that negative charge is delocalized. So now we have a less charge dense region, so we have a weaker nucleophile. This guy has more dense negatively charged region, so therefore this is a stronger nucleophile. Because again, nucleophiles are atoms with highly negative charge dense regions. So now let's compare this guy with this guy. Which of these two is a stronger nucleophile? And again, we see they have lone pairs of electrons, so that's a good sign that you have a nucleophile, because these lone pairs of electrons have negative charged electrons with negative electron density. But which of these is the better nucleophile? Because they both have lone pairs of electrons. Well, we know oxygen is very electronegative. So oxygen likes hogging all those negative charges, and it likes keeping those negative charges. So therefore, it doesn't want to donate these lone pairs to form a bond in the first place. So this is greedy and wants to hold on to those negative charge electrons because it's so electronegative. So therefore, it doesn't like losing its lone pairs of electrons. It likes to keep on. So therefore, it's a weak nucleophile. And this is a stronger nucleophile. It's less electronegative, so it doesn't mind losing its lone pairs of electrons forming a bond. So this is a better nucleophile than this one. And last thing, this is a pi bond. These pi bonds can also act as nucleophiles because again, we have these unhybridized p orbitals with these electrons in these p orbitals, so we have these negative charge electrons, so therefore this can also act as a nucleophile. So when determining if a compound is a nucleophile with localized negative charge, the first thing to look for is a formal charge. If you have a formal charge of -1, you're probably a nucleophile. And what is a formal charge? What does it mean if this oxygen has a formal charge of -1? It means it has one more electron than protons. It has more electrons than protons, one more electron than the amount of protons, so therefore it has a negative charge of formal charge of -1. So that's the first thing. If a compound has a formal charge of -1, it's probably a nucleophile. Another thing is looking for lone pairs of electrons. If it has a lone pair of electrons, it can probably donate those electrons and act as a nucleophile. But we learned just because two atoms have lone pairs doesn't mean they're the same strength in nucleophilicity. The electronegativity of the atoms also has an impact. And also pi electrons. If we have pi electrons, we have negative charge electrons which can act as a nucleophile. So those are the things to look for nucleophiles. What about electrophiles? We know these are all electrophiles. These are all electrophiles. So, and again, the key theme between them, what they have in common is these positive charges. But this example, this carbocation has a formal charge of +1. So this has highly positive charge dense regions, so this is a very strong electrophile. This guy also has a partially positively charged carbon, but it's just a partial positive charge. And why is this carbon partially positively charged? Because it's bonded to all these electronegative atoms, pooling electron density, stealing the electron density from this carbon. So then this carbon has an electron deficiency, so it's partially positively charged. So we have a partial positive charged carbon, so that's a good electrophile. And the same thing here. And again, the same thing here, but again, the more oxidized the carbon, the stronger an electrophile. For example, this carbon is more oxidized than this carbon. So because this carbon's more oxidized, it's a more stronger electrophile, and it has a more partial positive. Because again, it's more oxidized, so it has more bonds to these oxygens, stealing electron density, creating a partial positive, so therefore creating this electrophilic carbon. Well, this one has less bonds to these electronegative atoms, so therefore there's still some electron density being taken away, but not quite as much, so we have a smaller partial positive. And then these guys, what's going on here is, again, this carbon is oxidized, but again, we see comparing these three, this is the most oxidized, so this is the strongest electrophile, this is the least oxidized, so this is the weakest electrophile, but it's still an electrophile, and this is also an electrophile. Why? Because again, these atoms are very electronegative. For example, looking at this guy, this chlorine is more electronegative than carbon. So therefore, it's stealing and pulling electron density towards this chlorine, stealing that electron density, creating an electron deficiency, so creating a partial positive, so creating this electrophile. So when looking for electrophiles, the first thing is look for a formal charge of +1. If, for example, if you have a formal charge of +1, you have a high positive charge dense region, so you're a strong electrophile. The next thing to look for is those electronegative atom interactions. If one atom is much more electronegative than the other one, it will pull electron density, creating a partial positive, and therefore creating an electrophile. And again, so those are the common things to look for. And again, just look for oxidized carbons. That's a good sign that it's an electrophile if you have an oxidized carbon. So again, these are a couple of common examples of electrophiles you'll see. But again, the reason why these reactions occur at all is, again, because we have partial negative compounds with their negative charge dense regions, and we have partial positive charge compounds with their positive charge dense regions. So those charges want to destroy each other. Just randomly, if we have, again, let's just randomly choose these two guys, we know they'll react. This negative region will react with this positive region. Those charges will destroy each other. They'll form a bond destroying those charges, which is stable. And that's most of the time why we have reactions reacting. So now I want to go over a different example. So let's say we have these two compounds. Let's say we have this compound. Let's say we have this compound. If we have these two compounds in a beaker, will they react? Well, let's think about it. This compound has a partial positive. On this carbon, because again, it's an oxidized carbon, so that's a good sign. It's an electrophile, because this oxygen is pulling electron density, so we have a partial positive. What's going here? Well, again, we have this lone pair of electrons with some negative charge dense region. And again, we know this isn't the strongest nucleophile, because again, oxygen is very electronegative, but again, it does have a lone pair of electrons, so it's a weak nucleophile, but it is a nucleophile. So we have a negative charge nucleophile and a positive charge electrophile, so we know they can react. But again, we have a pretty weak electrophile. And we have a pretty weak nucleophile. So how can we promote this reaction from occurring? Well, if we can make this guy more positive and therefore become a stronger electrophile, that can promote this reaction. And for us, luckily for us, we can do that. For example, if we made the solution more acidic, we know we would have more of these positively charged protons, usually in the form of hydronium. But again, if we made this solution more acidic, we know we have more of these positively charged protons, so therefore we could protonate this oxygen. And when this oxygen gets protonated, these lone pairs essentially form a bond with hydrogen. creating this this formal charge of +1 on this oxygen. So essentially, we're making this compound more positive. And now that it's more positive, it translates to this carbon becoming more positive. So now we have a more positive carbon, so therefore we have a stronger electrophile. So that's one way we can promote this reaction. So again, the point is, acidic solutions create stronger electrophiles, and therefore increasing the reactivity, and therefore promoting this reaction. However, what if we made the solution more basic? What if we added some bases? Well, if we made the solution more basic, this base could steal this hydrogen. And when they steal this hydrogen, what's left? We steal the hydrogen and we create this guy. This guy with this formal charge of -1. So now we've really created a good nucleophile. Now we really have a good nucleophile. So again, this is much more negative now. We have that formal charge of -1, so now that can promote this reaction because we've essentially increased the reactivity of this guy promoting this reaction. So the point is basic solutions can promote reactions by creating better nucleophiles. So again, that's why we can use acid and bases to catalyze reactions. We increase the reactivity because again, most reactions you see in organic chemistry, when you have two compounds and you're wondering how are they going to react, just look, can you see partial positive or fully positive charge regions? Or can you find partial negative or fully negative charge regions? And if you do, you know they can react through these electrophile-nucleophile interactions.